Alrighty, howdy everyone. How was everyone's break? Feeling okay? Yes. Okay. Hope everyone relaxed and had a good time. Welcome to your last almost in class exam. Are there any questions for me before we get started today? No? Okay. Did everyone see my announcement with how to calculate your grades? Yes. Does that make sense how you do it? Yes. Yeah. Okay. If you have any other questions on that, just let me know. I would make a distribution, but that would take me like half a day. And I have a lot of things to be doing. So just if you have questions on like where you think you are, refer to that last slide from the intro slides. Dr. Lindahl says like he has like 2 A's, 2 B's, whatever, and he kind of goes through how you average them and whatever. Just reference that and that'll help you see what kind of letter grade you have right now, but you can look at a numerical grade in terms of how many points out of 100 you have. And then you can base them off of a distribution from exam 3 or 4. Look at one of those because I think those have like slightly different distributions. And if you fall in between a range, and you're probably on the cusp of a A or B or a cusp of the B or C. But that's just grade stuff there. If anyone's missing an exam, just let me know. Just keep on emailing me. I get a lot of emails throughout the day, but I hopefully will respond to all of them as quickly as I can and make sure you have all of your grades in. And I should hopefully have these grades in by whenever Dr. Liddell offers the makeup exam. Yeah.
Do you know when lab grade, like they have to grade those books?
I don't. They probably have all of next week in order to grade them. Yeah, they should have through the 10th to grade them, maybe into like the 11th or 12th. Any other questions? Alrighty. Stick with the usual of going over the homework. Does that sound like a plan? Alrighty. So starting with question 1, when charging your phone, the battery essentially is an electrolytic cell. Is that going to be true or false?
True.
Yes, that will be true. When it is not charging, what kind of cell is it? Heard a couple answers. Who's confident? Yeah, galvanic or voltaic. That's good. Yep. So, right, you're an electrolytic cell when it's charging because you're moving electrons one way, and then as you're using it, those electrons that you built up are being used to power your phone. Okay, when it's charging, electrolytic cell. Okay. Question 2, for the electrolysis of water, the net reaction is 2 waters splits into oxygen and hydrogen. Is that going to be true or false? This is true. Yep, that's the exact balanced equation that we're looking for. You want to make sure that it is balanced in terms of the electrolysis of this. But that electrolysis, whenever you see lysis, it's going to be splitting. So you want to break an atom or break a molecule. So this will be true. Okay, question 3. A concentration cell has no driving force under standard conditions. True or false?
True.
That is going to be true as well. Can someone tell me why it's true?
Because it's the same concentration, the same stuff and stuff.
It's not going to be the same concentration. Your concentration differential is what's going to actually make the E cell. But the E naught of the cell, it's the same material. So one thing's getting reduced and one thing's getting oxidized, but that same thing is getting reduced and oxidized. So in terms of E naught cell, it's going to be E naught cathode minus E naught anode. The values you plug in for E naught cathode and E naught anode are going to be the same. So that'll always end up as 0. So that standard condition of the E naught of the cell for concentration will be 0, but that E cell, right, non-standard conditions, that concentration differential is what charges that. Questions on 3? Okay. There's an example of that later on too. Question 4, for a metallic electrode, the metal atoms are positioned in a 3D lattice with some valence electrons not bound significantly to any particular atom. This is also true. Okay, if we think about metallic bonding, that's in the PowerPoint slides that Dr. Lindahl has. but you can think of like that valence electron as not necessarily tied to a specific atom within that metal sheet. So those will all be just flowing throughout your metal. Questions on 4? Yep.
So does it mean for all metal electrodes that will always form like a
Yeah, pretty much. Anything within like that transition metal period or transition metal block, those are all going to be free flowing electrons. Yeah. Any other questions? All good questions. Okay. Question 5. Which of the following statements are correct? So for question 1, we have E0 cell values change when the concentrations of a species in the electrochemical cell change. Is that going to be true or false?
True.
Oh, I heard both. Who's really confident?
I don't know what I'm talking about.
Yeah. Zero cell, like based on, like the concentration doesn't matter because the values are just given, you don't change them.
Yes, yep. So for under your standard conditions, so emphasis on the standard or that not of the E0 cell, this will be false. Concentration doesn't matter under standard conditions, right? If you have a whole bunch of aluminum or you have a little of aluminum, that same electrode is going to produce the same reduction potential. Okay, so it doesn't matter how much charge is there or how much concentration is there. Yes.
So nothing technically taken?
Yes, nothing will change this. It'll always be this reduction potential. Any questions on 1 being false? Okay. Question 2. That redox reaction is an N6 redox reaction. How do we find that out? Yep, we need to kind of look at our oxidation states and balance our oxygens. So we can write out this. So I broke this into my half reactions first. And whenever you're breaking your redox reaction into half reactions, you always want to keep your same non-oxygen elements together. So in this case, our carbons are going to stay together. So I'll have carbon monoxide and carbon dioxide. If we're just looking at the carbons, what is the oxidation state of carbon in carbon monoxide? +2. Because what's the oxidation state of oxygen? -2. When is the only time oxygen is not -2? Good. In hydrogen peroxides, oxygen is what? -1. Perfect. Okay, so then what's the oxidation state in carbon dioxide? +4. Right? Oxygen is going to be -2, and we have 2 of them. So the net of those oxygens is going to be a -4. So we need carbon to be +4. So was carbon oxidized or reduced? This was oxidized. What's the N for this reaction specifically? This is 2. What's our other half reaction? Good. What's our oxidation state on iodine on the left-hand side? +5. What's the oxidation state of iodine on the right-hand side? 0. Yep. That's its elemental state. It likes to hang out as diatomic iodine. So that'll be 0. So is iodine oxidized or reduced? It was reduced. What's the N for this specific half reaction? N is 5. So what is the N for our combined reaction? It would be 10 because we need to make both of them equal. So we need to multiply this whole thing by 2 and this whole thing by 5. So we would have an n of 10. All right, we want to find the, what is that? Least common multiple. So is statement 2 false or true? False. Questions on splitting half reactions or anything like that? Yes.
I'm still a little confused how you find oxidation state.
Yep. So a couple things on oxidation states is there will always be a couple of general rules that will help you find other ones. So one of our rules is that oxygen will always have a oxidation state of -2. The only time is when it's in hydrogen peroxide, and that's because hydrogen always has a +1. And so hydrogen peroxide is H2O2. So in order for oxygen to have a balanced oxidation state, hydrogen will have +1. You have 2 hydrogens at +1, so that's going to be +2 total. Since we only have 2 oxygens, we can't have both of those be at -2. They have to equal out that +2. These will just be -1 for a -2 total. That's hydrogen peroxide. But overall, your oxygens will always have a -2 oxidation state. So very similar, like how we use coefficients and everything for balancing our reactions, you need to balance your oxidation states. So in our carbon monoxide first, we know that oxygen is going to have a -2 oxidation state. So that first singular oxygen has -2. If there's no charge on the molecule, then your oxidation states need to equal that overall charge. If there's a charge, then your oxidation states need to equal that charge too. But since there's no charge, that means 0. That means our oxidation states need to balance out. So they need to add up to a 0 charge. So in order to find what carbon is, you're basically saying, okay, X plus -2 equals 0. What oxidation state will get me to this neutral charge? So if you solve for X, then you get X is equal to 2. So you know that carbon has to have a +2 oxidation state, okay? Then the same thing for the carbon dioxide, right? We have oxygen is -2, but we have 2 of those. So then you have to multiply and say, okay, we have a total of -4. So now carbon is X plus -4. Oops. Is equal to 0. Does that help?
Yeah.
Okay, and then to finish off question 5, a concentration cell can only have an electrochemical cell potential under non-standard conditions. Yes, that's true. So D would be your correct answer as the only statement that is correct. It'll be written out in the same way, yes. It's an electrolytic cell. Yeah, that's just that. Yeah, they all have very similar, or they're all like the same thing pretty much. It's just how you write them and what you're using in terms of your anode and cathode. It's confusing. Any questions on homework question 5? Yes. Yep. So when we look at a concentration cell, I'm gonna scroll up here. You would have something that looks like maybe it's Ag plus, and this is at 0.2 molar. This is gonna go to Ag solid. This would be Ag solid. It would look something like this, where you have your anode is this gold thing, and then your cathode is another gold thing. but they're at different concentrations. So under standard conditions, if we want to say, okay, this is our anode, this is our cathode, the reduction potential for both under standard conditions, both gold anodes or cathodes would be the same. We would say that, I don't know if this is written up here. Yeah, it is. Right, your AG is the 0.799. Your AG plus an electron goes to AG solid, has an electro potential of 0.799 volts. That's the same for both the anode and the cathode. So if we solve for E naught cell, we're plugging in 0.799 into both of those situations. Therefore, under standard conditions, E naught of the cell is equal to 0. Okay. Under non-standard conditions, we now have to look at this concentration component. And because we have different concentrations, that gradient is going to push one from the other. Does that help? Yes. They're all like kind of the same thing. Yeah. So when we look back at statement 3, we're saying that a concentration cell can only have an electrochemical cell potential under non-standard conditions. That has to be true because a concentration cell means it's the same anode and cathode material, but different concentrations at the anode and cathode. Does that help? Yes. Yes. Yep. Yes. 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 Yep. Yes. Yes. Anything else? Question 6. Which of the following statements is correct? So this time the E cell values change when the concentrations of species in the electrochemical cell change. Is this true or false? This is now true. When we look at E cell, we're now looking at your Nernst equation. And your Nernst equation is saying this is E cell is equal to E naught of the cell minus 0.059 over N times the log of Q. As concentration changes, what changes in this equation?
Q and N.
Q and N will change. N will, I don't think N will change. N shouldn't change, but Q will definitely change.
And then
N is the number of electrons. So since it's the same material, the same number of electrons will always be.
it's like a rate amount of like electrons.
Yes, yep.
Because if you put in more, it will just adjust.
Yes, yep,
So that-
yep. So N should stay the same because you're just transferring the same number of electrons, but Q will change because you're worried about concentration. So as concentration changes, that minus component will change. And what did we say E naught of the cell for a concentration cell is? Yep, this would goes to 0 in a concentration cell. So the only thing that's dependent on what E of the cell is what that concentration of those two species are. Yes, yep. Because then it only is driven by the concentration of the cell. That's either like your galvanic or voltaic cell. Yep. Yes. So that's this portion up here where we're saying that the concentration cells, it's the same material. So the E naught of the cell under standard conditions is 0 because it's going to be the same reduction potential minus the same reduction potential. Any other questions on statement 1? Question or statement 2. If KEQ is greater than 1, E naught of the cell must be greater than 0. Why is it true? Yep. So it has to deal with spontaneity. If your KEQ is greater than 1, what is favored, products or reactants? Products are favored, right? This is driven towards products. And if you're driven towards products, that means that a reaction is happening. And so you're going to be producing some sort of E potential. So this is true. This also relates to like the equations of like E naught referring to delta G and delta G relating to K. Any questions on statement 2? Alrighty. And statement 3, a coulomb is the amount of charge associated with 1 mole of electrons passing through a wire with a current of 1 amp.
Yes.
This is false.
Oh, it was an amp.
Yes, a coulomb is an amp times second. It is the how many charges pass in 1 second with 1 amp traveling. Say it again. In what do you mean? Like in what sense? Oh, bottom of the notes. Let me look. Oh, yes. So when you're counting electrons, that's where your coulomb comes into play. It's saying how many physical electrons are passing through the wire at that time. In order to, but that does not directly relate to electricity. Electricity is how much over time you're using. So that's where Faraday's constant and then amps come into play, because then you can relate how many moles of electrons you have to how many you're actually counting. I can explain that in a little bit, and that might help with it too. Go ahead.
For this one, would it be like the Faraday's number of coulomb equals 1 mole?
Yes, because Faraday's constant is 96485 coulombs per mole of electrons.
Is that at 996,485 seconds, like a day?
Yes, yep, that's in 1 day. Any other questions? Okay, so for question 6, we said that our answer is B. Only 1 and 2 are correct. Alrighty, question 7. We want to balance the reaction. Iron oxide and carbon monoxide produces iron and carbon dioxide in an acidic solution. Make sure the coefficients of the balanced equation are at the lowest possible integers. And in this case, the coefficients for CO2 is what we're looking for. Someone tell me how we do this. Go ahead. Yep, so we're going to break them into our 2 half reactions. So what's 1 half reaction? And what's the other one? So when you're balancing your half reactions in acidic or basic solutions, there are a plethora of steps that you can take in order to find what you're looking for and how to solve to get to the final answer. I personally like to solve anything that's not oxygens or hydrogens and balance those first. So if I'm looking at my two half reactions, I'm going to look at my iron and balance that. And then I'm going to look at my carbon dioxide and balance that, or carbons and balance that. So in the left-hand reaction, I have 2 irons on my left-hand side and 1 iron on my right. So I know that I need a 2 in front of that iron. So we end up with 2 Fe as that first step. In the carbon situation, you have carbon monoxide and carbon dioxide. Those carbons are the same. And so you can just keep it as carbon monoxide and carbon dioxide. I then balance my oxygens. So looking at the iron half reaction, I have 3 oxygens on my left-hand side and no oxygens on my right-hand side. So I know I need to add what in order to balance those reactions. We need to add 3 waters. So I'll have iron 2O3. And then what do we need to do to the carbon half reaction? We're going to add 1 water to the, yes. Okay, now that I've balanced my oxygens, I've now introduced hydrogens into the system. So now I'm going to balance my hydrogens. I added 6 total hydrogens on my product side for my iron reaction. So I need to add 6 H+ ions to the left-hand side. So we'll end up with 6 H+, your iron, and H2. What about the carbon half reaction? Yep, we need to add 2 to our product side. We've now introduced charge into the half reactions. So now I need to balance that positive charge with our electrons of our negative charge. Where are we going to be adding electrons for the iron half reaction? Yep, we need, so what side has more positive charge, the reactants or the product side? The reactants. So we need to bring that side down with the negative charge to get to that neutral. We have 6 positive charges, so we're going to add 6 negative charges to our half reaction. Yes, right. So none of the other molecules in this half reaction have charge. If they did, then we would take that into consideration. But the only thing with charge in our half reaction is that H+ at the moment. What do we do to our, yep, minus plus. There's an example after this, I believe, that I'll show you that. Then what about our carbon half reaction? What do we need to do for that one? Yep, perfect. So we'll have two H+ and 2 electrons. So now looking at our electrons being transferred between our 2 half reactions, we have 6 electrons in our first one and 2 electrons in our second one. So what do we need to do in order to balance those? I think I heard someone say multiply by 3. Yeah, that's going to be our easiest one. We're going to multiply this whole reaction by 3. So we end up with 3 H2O, 3 CO, 3 CO2, 6 H plus, and 6 E minus. So now our electrons being transferred between both half reactions is the same. You can combine these and you can, right, cancel out your hydrogens, cancel out your electrons, and find your overall overall reaction from your half reactions. But we are looking for the coefficient of carbon dioxide. Do we have that now in its balanced form? Yep. So what's our coefficient? 3. No, it doesn't really. Yeah. Yeah. Yep. Yeah, go ahead.
So which one do we use for like N? If they find it?
So if we were to find N, you want it when it's equal on both sides. So when both of your half reactions are equal in number of electrons being transferred, yep. So we would say that N is equal to 6 here.
So we can add balancing, but then the electron balancing.
Yes, that's what I personally do. So that you have everything balanced and then you deal with charges. Yep. Yes, yeah, you could totally do that as well.
And then does it matter like where the
No, I think he does like electrons first. I hate that actually. So I do that. I do electrons at the very end because I like everything else balanced before I introduce charge. But it's just a personal preference. Whatever works for you. There's multiple ways that you can get to the right answer. Yeah. Yep.
How do we know that?
Like why can't we just go like this at the very beginning? Because now you've introduced a 2 in front of your carbon. So that means you now have to go play with the 2 in front of your carbon on the carbon dioxide. So then if you put a 2 here, that now screws up your oxygens again.
But the oxygens aren't equal like at the beginning.
Yeah, so that's why we introduced the water into our half reactions. Because then you have that extra
So you worry
component.
about everything except for your
Yes,
there
yeah.
you go.
Yep, so that's why I said we can just move that on to the next row because everything but oxygen is balanced already. Yep. Any other questions? Okay. Question 8. We're going to balance the half reaction in a basic solution this time using minimal integers. And we have the half reaction listed there. And this time we're looking for how many electrons are transferred. So we're looking for N. Okay. So again, there are multiple ways that you can solve this. If you look at oxidation states and do it that way, by all means, I will show you how I do it using like the steps that we just did, but this time for a basic solution. So if you don't want to listen to that, by all means, turn me off. Okay. So the first step that I do when we're trying to solve for a balance and a basic solution is again, solve or balance anything that's not oxygen or hydrogen. So in this case, we're just looking at the chromium. We have 2 chromiums on the reactants and 1 chromium on the products. So I'm going to put a 2 in front of my chromium. So I have 2 Cr3+. I'm then going to look at my oxygens and balance my oxygens. I'm going to do that by adding water to our system. I have 7 on the reactant side, so I'm going to add 7 waters to the product side. I just introduced hydrogen into the system, so now I have to balance my hydrogens with H+ ions. I put 14 hydrogens from my waters, so I'm going to add 14 H pluses. Yeah, go ahead. Yep, so you'll see what I do here. So I added my H pluses to balance out my hydrogens. This is a basic solution, so when you have H pluses, you don't want those in a basic solution. You have to neutralize them with hydroxide ions. So since I added 14 H pluses, I'm going to add 14 hydroxides to both sides. So I'll have 14 OH minus. And then everything else is the same. And then 14 OH minus on my product side. So then, yes, yep. He might do it where he doesn't add the water first or something. I haven't looked at his notes too closely on that portion. Just because I read through them, I said I do that different. So I just kind of glanced past it. Okay, so now we have 14 OH minus and 14 H plus. What is that going to do? It turns into water. So now we have this combining, and I'm running out of space, but that's fine. So now we have 14 H2O Cr2 O72 minus 2 Cr3 plus 7 H2O and 14 OH minus. Okay, we now have hot water molecules on both sides. We have 7 on the products, 14 on the reactants. So I cancel those out and say this is 7 H2O. Yes. Yeah, for acidic solution, you just leave it as H plus because they'll be free flowing H plus in solution, or those will be in majority. With the basic solution, your OH minus will be in majority this time. Alrighty, now everything is balanced on both sides. So now you can just look at your charges. So on the reactant side, how much charge do we have? We have -2, and that comes from your chromium and oxygen complex. So I'm just going to put that in red. How much charge do we have on our product side? It is -8. Where did that come from? Good. So we have 2 chromium ions that are at 3+ each. So that's going to be a +6. And then we have -14 from our hydroxide ions. So this combined will give us a total of -8. So where are we going to add our electrons? Yep, we have to add them to the, I say left, my left. We have to add them to the reactant side. And how many do we have to add? You have to add 6. So overall, we'll have 6 electrons, 7 waters, 1 Cr2O72 minus, 2 chromium ions, and 14 hydroxides. So what is N? 6. And that's for question 8, not 9, even though we ended in 9. Yep. So in the red, we have -2 on our reactant side, and we have a total of -8 on our product side. So since electrons are negatively charged, we have to bring that more positive side down. So we're just looking for what can we add to our -2 to get to -8. Yep. Yes. You tell me, what side are your electrons on? So this is a reduction reaction, and in order to find what side is more positive, you have to look at your oxidation states. So what's your oxidation state of chromium on the product side? The product side of chromium is, yep, is +3. So I'll put that in. This is +3. What's our overall? So what is oxidation state in general? -2. So how much oxidation do we have for our oxygens? Yep, so this would be -14. So what's your chromium oxidation state? +7. So we're saying chromium is going from +7 to chromium +3. So do we get more negative or more positive? We get more negative. Yes, because we have the -2. So it would be +6. Sorry, I was just looking at chromium. Yep. Yep, so in that step, we have 14 here and 7 here. So since they're on both sides, it's like saying you have 14x is equal to 7x. So if you subtracted 7 from the right-hand side, then you would have just 7x left over. Yep. Yep. So the last problem, we were in an acidic solution. So we want an overall H+ positive charge. But in our basic solution for question 8, base refers to the OH minus. So we want those to be in excess, whether our H+ to be in excess. You can always add H+ for the basic, but you just need to neutralize it with the OH minus.
But you don't use OH.
For the acidic. Yes, yep. You have just one extra step for the basic. Yes. Yep. And then it's just like, if in basic, do this next step. Any other questions? More you practice, you'll get really good at these. Okay. We're gonna move on. Question 9, we're going to balance the following reaction in an acidic solution this time with minimal integers. And I want to know how many water molecules are in the balanced reaction. Okay, so this time we're given this time we're in an acidic solution, but we're given the full reaction. So we have to break this up into 2 half reactions. So what's going to be 1 half reaction? The Te, the selenium. And the other one's going to be what? Okay. So same steps we just followed, except this time we don't need to add that OH minus component because we're in an acidic solution. So we're first going to check for everything that's not oxygen or hydrogen. For selenium, those are fine. For our nitrogen, what do we need to do? Yep, we need a 2 in front of the NO3. How many water molecules do we need to add to the selenium? Yep, we'll have 3. And where are we adding waters to our nitrogen one? Yep, we need 2 of them on the left. Right, when we added that 2, we now have 6 oxygens on our products, but only 4 on our reactants. We're going to add 6 hydrogens to the reactants. For our selenium, and we're going to add 4 electrons to the product, or sorry, 4 protons to our nitrogen. We do not need to add hydroxide ions because we are in an acidic solution. How many charges do we need to add into what side for our selenium? It would just be 4. Good. Yep. Question.
Why would you not have water to the right side?
So when we added the 2 in front of the nitrogen, we've now introduced 6 water molecules. Yep. Yep. And so I heard 2, 6, and 4 for electrons. And it is going to be 4. We have a 2 minus in our TeO3 2 minus, right? So that has an overall negative charge of 2 minus. And then our 6 hydrogens have an overall charge of +6. So +6 plus -2. If you followed that would be +4. So we'll add 4 electrons to our selenium. And then what about our nitrogens? I'm sorry, I missed a minus this whole time, so yes, it is 2. NO3 minus has a minus on it. I didn't copy it when I first wrote my half reaction. So what do we need to do to our electrons to balance them? Yep, so we'll need to multiply this whole reaction by 2. Yep. Yep, so we have this NO3 minus has 2 negative charges, and then our H plus has 4 positive charges. So 4 plus -2. Okay, and then this question is looking for water molecules. So we have 4 water molecules on our reactant side, and then 3 water molecules on our product side. So what's going to be our overall water molecule situation? We'll have 1 on our product or reactant side. So it will be 1, and your overall reaction, I'll write it up here, is going to be H2O. The TE one? Yep. So we have 6 H pluses, so that's a total of +6. And then we have the TeO3 has a 2 minus, so that's a total of -2. The
Like the O3,
nope, because that's for the whole reaction, or for the whole molecule, so it's only given for that molecule. Yep. So it's just going to be an overall of -2. So you'll have when you combine those, then you get a +4. Any other questions on half reaction balancing? Yeah. Any other questions? Just help make sense a little bit? Yes? Okay. Are we ready to do electrochemical cell stuff? Okay. Question 10. Question 10 is asking, consider the cell. We have silver concentration, whatever, and copper in a electrochemical cell. And what is the E cell for this cell at 25 degrees Celsius in volts? So is this E cell going to be standard or non-standard conditions? This is non-standard conditions. So what equations would you immediately think of if you're in a non-standard condition? You should do the Nernst equation, and who can tell me what the Nernst equation is? Yep, perfect. Okay, so that's your Nernst equation. That one's super important to know. And then if we're talking about your notation of this electrochemical cell, when we're given this silver component here, what portion is that? This is going to be the anode. And what is going to be this portion here? Yep. Your second half is going to be your cathode. Okay, so I remember this as alphabetical order. It's going to go left to right, A to Z. This, in this case, is just A to C. Yes. Yes, it'll always be written anode and then cathode. Yep. What happens at the anode? What reaction? Reduction or oxidation? Yep, this is going to be your oxidation. And then what about your cathode? This is going to be your reduction. Okay. So if we're going to write out the reaction that's happening, how do we do that? You can do, we can write out the full reaction first. We don't need to split into the half, because we already technically split it into the half reactions by writing it as anode cathode. So we can just write the overall equation. Yep, so we need gold solid. Yep, copper ion. Oh, that sucks. So we have gold solid and copper ion, and what is that going to form? Gold ion. Awesome. And copper solid. Right, so the important thing to know is that we're doing anode and cathode. So your anode is always going to be oxidation, which means that we need to get more positive in our oxidation number. So you're going to go from solid to ion here, because you're going from an oxidation state of 0 to +1. For your copper situation, you're doing your cathode, which is the reduction potential, which means that you have to get more negative in your oxidation number. So we want to go from your positive portion to your more negative portion. You can also look at this and saying, okay, I know my cathode is reduction. Go look at the front page of your exam and say, here are all of my reduction potentials, and say, okay, copper needs to be reduced. What does that reduction potential look like? And you'll see that it goes from copper into electrons to your copper solid. Then, at least you have half. So you just need to do the opposite for the other one. Does that make sense on how we wrote this out? Okay. So now that we have this, we can solve for our Nernst equation. What do we need to know first? Yes, we need to know our N and our E0 value, or E naught value. Okay, so we need to make sure first that our equation that we wrote out is balanced. Can anyone tell me easily without breaking it into the half reactions what we need to do? We just need to add a 2 where? Yep, we need to put a 2 in front of the gold. If you look at just charges here, since it's only like 2 components, we have a +2 from our copper going to 0, which means that we are losing 2 electrons or gaining 2 electrons there. But your gold is only losing 1. So we want to make sure that that 1 to 2 is matched. So that's why it's going to be a 2 in front of both. So what is N going to equal? N will equal 2. Okay, and then how do we find E naught of the cell? Yep, we're going to use our E naught cathode. Wow. So we have our E naught cathode minus our minus our E naught anode. And we're going to use the chart at the big top of our page in order to know what those values are. This copied over really poorly onto my iPad. So I started writing them out so that they're just going to look like this. It'll be nice and pretty for you. Feel free to detach that when you're taking your exam for when you need it. I don't know if I got the copper down. I don't think I did. But we do have gold, so we know that gold is going to be this one here, the 0.799. And then is the 0.799 going to be your cathode or anode? Yep, it'll be your anode. And your cathode is 0.337. And this is 0.7. So your E naught of the cell will be 0.462. Your reduction potentials, if you use them as is, you can use this equation as is. This is E cathode minus E anode when you use reduction potentials. So you don't need to flip it to negative or positive. You can just use them directly. Nope. To flip it. Yeah. I don't know, because he likes to make things complicated. Yeah, if you just use E cathode minus E anode and you use the reduction potentials, it'll get you your E naught of the cell every time. Yeah. Yep. So it would be positive here. I'm sorry, it would be negative. It is negative. Any other questions? Yep. It doesn't necessarily have to. We can have something that's powering it through it. It might have an extra power source in order for it to work. That's just not pertinent for this question for you to know. But it doesn't necessarily have to be. If it's positive, then it's spontaneous. If it's negative, it just needs some extra help.
Per se, like the E zero cell was positive, wouldn't the negative in the equation, like your E cell negative? You have E zero cell minus.
Yes. Yes. So if this was a positive reaction, then it would be written the opposite way, where the copper would be getting oxidized and the gold would be getting reduced. Yep.
Silver gaining one electron.
The AG here is giving up an electron because it's getting more positive. So as we look from this AG here to this AG here, we go from 0 to +1. So we're losing an electron in that case. Like what I have highlighted. Yep. So it'll always be written as your anode first and then your cathode second. So the two lines splits your anode and cathode. Does anyone know what those two lines indicate? Yep, that's going to be your cell bridge. Okay. So once we find the E naught of the cell, we can then use that in our Nernst equation. So we have E cell is equal to negative 0.462 minus 0.059. What did we say N was? 2. Then we have our log. What goes on top in your Q? Yep, it'll be your 0.25 squared because we have a coefficient of 2 in front of our gold ion. And then we'll divide this by the 0.049. Yep.
I know which one to put on top of it.
Yep, so Q here is going to be the same as like all of the other Q's and K's that we've done. So it'll always be products over reactants. That's why you write out the whole equation first. So then you know that your gold ion is in the product side while your copper ion is in the reactant side. Yep.
You wouldn't have to multiply by 2 and then so.
No, because we're saying that your equilibrium your equilibrium concentration is the 0.25. Yep. Most of y'all have fancy calculators, so this doesn't really pertain to you. But if you're using one like me, that's a little bit less intense. I would recommend squaring your 0.25, dividing by the 0.49, taking the log of that, multiplying by 0.059, dividing by 2, and then subtracting that from the negative 0.462. That will be easiest. And so then your E cell would be negative 0.436, which is C. Yep. Yeah, so you can right, you can do that fraction first if you want to, and then just have one number that you're multiplying by the log. What questions do we have? Yes. How we figure out Q? Yes. Yep. Yeah, so we're looking at, I'll highlight it because there's a lot going on. We're looking at this reaction here in order to find what Q is. Any other questions? Okay. The next one. Question 11. We're doing a lot of this, so if you have questions, maybe it'll clear up in the next couple as well. So for question 11, we have one half cell in a voltaic cell. It's constructed from a silver wire electrode in a silver nitrate solution of unknown concentration. The other half cell consists of zinc electrode in a 1 molar solution of zinc nitrate with a potential of 1.3 with zinc nitrate period. A potential of 1.35 volts is measured for the cell. What is the concentration of silver ions in the solution in molar? Yes. Yes. Yep. So that's one important thing to know is that voltaic is spontaneous. So we're looking for a positive or negative E cell. We're looking for a positive E cell. So when we write out our reaction of what's happening at the anode and cathode, we want to make it so that our E cell ends up positive. Okay. So we know that we have silver and we know that we have zinc. So this is where you look at your, maybe I have both of these. Sad. I wrote it down, so I'll just bring it down here. So you look at your silver and zinc. So you have Ag plus say it again. No. Nope. Okay. So we have silver, which is 0.799 when reduced, and zinc, which is negative 0.763 when reduced. Which one is going to be more likely to be the reduction potential? This silver, right? So we want silver to be reduced, which means that zinc is going to do what? This one's going to get oxidized. Okay, so if we're going to write out our overall reaction, these are in reduction potential, so we're going to keep silver as silver. So we'll say this is Ag plus. We're going to flip the reaction for the oxidation. So then we'll have the zinc solid as our reactant. Silver again is staying the same, so that's going to go to silver solid. But then we flipped the zinc reactions. This is going to be Zn2 plus. So now we've written it out where that the silver is getting reduced and the zinc is getting oxidized. No, if it's negative, then it's as the reduction potential, it favors oxidation if it's negative. Yeah, so if it's in the reduction potential and it's positive, that means it's happy to be reduced. If it's negative, then it's happy to be oxidized. Yeah, go ahead.
We flipped it because we want to positive.
So we're flipping it because if we write out E cell. If we write it like this, whatever is the negative one, if we put that as your anode, then you have a minus, which makes it a positive. So that overall bumps up your E naught of the cell. And we're only flipping how we write it. We're not flipping the value of this. We just need to flip it in the terms of writing out the overall reaction because we need to have something getting reduced and something getting oxidized. So if we wrote it as zinc 2 plus and going to zinc solid, now we have both silver and zinc being reduced, and we can't have that. You need to have something being reduced and something being oxidized. Does that make sense? Okay. Yes. 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 Yep. Yeah. Yep. So if we're looking at the values here, I squeezed them in. Like this right here and this right here on this side. Your reduction potential for your silver is a positive number, which means it's favored to be reduced. And then your zinc is a negative number, which means it's favored to be oxidized. So if you plug those into the E cathode minus E anode, you get a more positive answer, or a more positive E naught of the cell, and that's more favorable. Since it's voltaic, we want it to be more favorable. Okay. Any other questions? Yes, yep, if both are positive, then you want whatever one is largest. Okay, so again, we need to find our Nernst equation and need to find the E naught of the cell, so we can do that now. So we know our E naught of the cell is going to be E cathode minus E anode. We said that the silver was the cathode, so this will be 0.799 minus that negative 0.763. So we get E naught of the cell equal to 1.562. Any questions on solving E naught of the cell? Okay, we're using that same Nernst equation again. So we have E cell, E naught cell, minus 0.059 over 2 log of Q. What is N here? 2. And why is it 2? Yeah, perfect. So just like the one where we just used the copper, where copper was +2, this time zinc is +2. So we need a 2 in front of both of our silvers. And if you broke those into the half reactions, you can follow that and prove that to yourself as well. Okay, so we said that this was 1.562. And we know that E naught of the cell from our equation is, or from our question, is 1.35. I would leave Q as Q for right now until you get to solving for Q. And I would plug in everything else, you know. So then you have 0.059 over 2, and you get the log. You end up with so if you subtract the 1.562 from both sides, you get negative 0.212. I just did 0.059 divided by 2 to get 0.0295. And then the log of Q. I'm going to divide by the 0.0295. So I get 7.186 log of Q. How do you get rid of logs? Base 10. So we'll call this 10 to the power of 7.186 is equal to Q. And this is 1534669. Now I'm going to write out Q. What's in our products? Zinc. What's our in our reactants? Anything else to silver? Square it. Yep. Okay, from our question, we know that the zinc electrode has 1 molar solution of zinc nitrate. what is that zinc nitrate going to do in solution? In terms of dissociation? It will dissociate. It will completely dissociate because we know that all nitrates always dissociate in solution. So how much zinc do we have in our solution? We will have 1 molar zinc. So we have 1, 5, 3. Right, we're looking for that silver concentrations. We'll just turn that into X. You can cross multiply by X squared and divide. So you'll end up with X squared equal to the value I can't find on my paper. Oh, I didn't even write it. And then you can take the square root of that value and you get X equal to 2.55 times 10 to the negative 4 molar. I think if you rounded sooner than I did, you'll get that closer to that 2.8, because I will round this to 2.6, but that is within the magnitude. Yep. Yep. So your zinc nitrate, since all nitrates are going to be 100% dissolvable or solubilized in solution, this will be zinc 2+ and NO3, 2NO3 minus. So if you have 1 molar of this, it turns into 1 molar of this and 2 molar of that. Yep. Oh, yes. Yeah, same thing. Yep.
But why doesn't it just keep the residual out there? You say that you have to like that.
Because
Back to the
yes, and so you are keeping your values the same, but when you're writing your reaction of what's actually happening in your cell, you need to show that something's being reduced and something's being oxidized. So the only thing that you're flipping is how you write this portion. So if you were flipped the other one and you kept the zinc the same, then you would end up in a negative cell potential, right? But because it's, yes, because then it would be negative 7 point. Oh, so then you would, right, if you flipped it, then it would be your anode and cathode switched. So then you would end up with a negative value. It would be the negative value of the E cell value.
That turns to negative, but when you switch to other one, then
Because it's all about this negative portion of the E naught of the cell. Yes, it's taking into account you saying this is actually being oxidized because you're plugging it into the anode, and at the anode it gets oxidized. So why are you confused? Right, because E naught of the cell, you plug in reduction potentials into your you're just flipping it to write it out. You're just flipping not the value, but the reaction that's happening. Yep. Yes, yep. You can't just put a plus sign here and add them. You have to reverse this one. Any other questions? We're almost done, I promise. Okay. Question 12. This is where the concentration cell comes into play, and you can kind of see the actual math of what's happening. But for question 12, we have the cathode of a concentration cell consists of a silver electrode dipped in a 0.1 molar solution of silver nitrate, and the anode also consists of a silver electrode, but in a solution of 0.02 molar silver nitrate. What is E naught of the cell and E cell in millivolts for this condition? Okay. So we have a concentration cell. We have one anode that is Ag plus an electron going to Ag minus, or just to Ag solid. And then we have another one because we need to have an anode and a cathode where we have Ag solid going to Ag plus and E minus. Okay, we said the cathode here is going to be the one that's the 0.1 molar. So which one, the top or the bottom, is going to be your cathode? The top one's going to be your cathode because this one is going to be the reduction. So if we're going to write out our reaction, we have Ag plus going to Ag plus and Ag solid, where these are 1 and these are 1. Yep. Yes, yep. So what's the concentration of that first Ag plus? Yep, it's going to be 0.1. That came from our question. And then the second Ag plus is going to be the 0.02 molar. Okay, so if we're going to write the E naught of the cell, again, this is still E naught of the cell is equal to E naught cathode minus E naught anode. Yep, it will just be 0 because your E naught of the cell, your E naught cathode is a silver reduction potential, which is still 0.799. And your anode is still the silver still the silver reduction potential, which is still 0.799. So under standard conditions, we get a E naught of the cell as 0, right? Nothing is happening under standard conditions. So 0 volts will also be 0 millivolts. In this case, you can just pick your answer and move on. But we're still going to prove that it's 41 millivolts as the other one, because it's not an exam and we have time. Okay, so again, we're still looking for the E cell, still the Nernst equation. This time E cell what is going to be our N value? Just 1, right? It's still silver. It's only giving up 1 electron or taking in 1 electron. We said that our E naught of the cell goes to 0. So we have 0 minus 0.059 log. What goes on top for Q? .02. And that means that your 0.1 will go on the bottom. Right, so 0, you can just ignore. This becomes a minus. So then you can just plug that into your calculator and you get 0.041 volts, which if you multiply by 1,000 will give you 41 millivolts. Yes.
When will E cell, because I know we talked up there, when will it not be zero? Or E not zero?
E naught of the cell is when you will have 2 different species. So like the last 2 questions we did, we had silver and zinc or silver and copper. Then we had an E naught of the cell because they're different reduction potentials. Here, since it's both silver as your anode and cathode, that's when it becomes 0. Yep. Um. I believe it's still same notation for standard and non-standard. I don't think that like the non-standard conditions throw it off enough to make it switch. Unless the original E naught of the cell is just very small. Yeah, I think it's still the same. Yep. Yes, yep, for concentration cells, your E naught of the cell is always 0.
But if it's non-standard, I thought this is non-standard.
It is.
Oh, okay.
Yep. So, right, we're saying that under the E naught of the cell, that will be 0. That's why on the left-hand side over here, the E naught of the cell is 0.
Oh.
So we can only solve for this under standard conditions. Because it's under standard condition, or sorry, it's non-standard conditions, we use the Nernst equation, which just inherently always has the E naught of the cell. So we're just proving that cancels out. Yes, yep. What other questions? Is it starting to make a little bit more sense on how to do all of them? Okay, I think we'll do 14 and then we'll come back to the challenge. If you want to leave, you can. It's not too bad of a challenge, but I don't think he'll ask you a challenge question on your exam. But don't quote me on that. I haven't seen them, so I don't know. But we'll do 14 together since that's not a challenge one. If you want to leave after that, by all means. If you want to stay and watch, or stay and go through that one, we can do that too. Alrighty. Question 14, we have considered the voltaic cell of the copper and silver. We want to know what is the E naught of the cell and the E cell for this cell. Wow, you say cell a lot. Okay. So which one is going to be your anode and which one's going to be your cathode? Perfect. So what's going to be your overall reaction that's happening? What happens at the anode? What happens at the anode? Oxidation. So which does copper solid or copper 2+ want to be on the reactant side? And what do we want to do for your silver? And then we'll have copper 2+ and you do something. Yes, perfect. Okay, so how do we solve our E naught of the cell? Does anyone remember what the reduction? Oh, sorry, go ahead. Yep. So what would you have to do? Yep. Does anyone remember what the reduction potential for silver is? Yep. Does anyone remember what we used for copper? You would have this on the exam, so yep. Right, so we end up with E naught of the cell as positive or negative? Positive, yep. So what kind of cell is this? Yep. Perfect. Okay, and right, this is a multiple choice question. So you can always look at your answer choices. Okay, can't be seen. You've already made your chances better. Okay, so that's one part of this question. We now need to find E cell. So again, the lovely equation we've just been using. E cell is E naught. What's our N here? 2. What's our Q equation? Is copper in your products, is copper ion in your products or reactants? Products. So that one's going to go on top or bottom. Yep. So that's 0.89. And then we have 0.48 squared. Yep. And so after some lovely calculator math, you end up with 0.44468, which is 0.445, which is B.
Ask us. The E cell using the high temperature and R constant.
He could if it's not at 25 degrees Celsius, but most of his questions have been at 25 degrees Celsius. So usually that's what you use. If it's not at 25 degrees Celsius, then you just have to use like Faraday's constant and the RT value. Any questions on the homework besides the challenge question? Okay. If you would like to stay for the challenge, by all means. If you would like to leave, I'll just give you a second to pack up your things. If you have any additional questions, just let me know. And I'll post this afterwards. Yeah. Yes. So I will have, I'm going to see if I can reserve this room again like next Wednesday, because I believe the first final's on Friday. So I'll try and do like another review session next Wednesday for the Friday people. And then I'll do one more like last minute review session on that Thursday as well. And that'll probably be what I do for the final for review. If you have the Tuesday final, then you just get more time to look at it. I would just do all of the practice problems you could ever do. Go back through your questions of your exams and right, anyone that you got wrong, try and see if you can get it right now. And then any ones that you got right, solve it backwards. Like flip out a different variable that you needed to solve for, or start from the, like solve it literally backwards and try and your answer, use that to find what you were given in beforehand. And then if there's like a big topic you don't know something about, you keep on having trouble with those, then I would just look up like that topic practice questions into Google and just see if like something else pops up. And then just recognizing those types of questions will help. I don't, but you have 2 hours to take your final and it's worth 150 points. So you can expect like 1.5 times. So right, they've been around 15, so maybe like 22, 23 questions. Maybe like, I would say something around there. I would assume he's going to have a couple more worked out problems rather than like more true false questions. But I'm not entirely sure. Yep. The Thursday will probably be the Zoom, but the Wednesday will be in person. Yep. Okay. Any other questions before we do the challenge? Okay. All right. So for the challenge question, we have a galvanic cell of aluminum and lead, and we want to find the E cell in volts after the reaction has operated long enough for the aluminum concentration to have changed by 0.4 molar. So we can assume a 25 degrees Celsius, and we can also assume that this change in 0.4 molar means that we're increasing the change of it. We're not reducing the change of it. Again, galvanic cell, it's still written as anode and cathode, so you can write out the equation for what's being reduced and what's being oxidized. Your aluminum is the thing that is getting oxidized as the anode. So we're getting more positive. So we're going to write this out as the aluminum solid and the lead ion is going to form aluminum ion and lead solid. Just basically looking at the charges of the lead and aluminum ion, you have +2 and you have 3+. So you need to balance those out. You can break this into half reactions where you have aluminum and aluminum 3+. Say this is 3E, and then you can say Eb2+, Eb solid, oops. And you can say 2E here. Sorry, that's gross. So you can see that we have 3 electrons and 2 electrons. You need to multiply by 2 and 3 respectively. So then in your overall reaction, you would have 2, 3, 2, 3. I don't think so. I don't think so. Because most of the time it's going to look like ion and solid and ion and solid. If anything, I think the most complicated is when he asks you about like silver nitrate or zinc nitrate, something like that. Alrighty, so now we have a balanced chemical reaction. So the first thing, right, if you're looking for that E cell, puts us to the Nernst equation. So we first need to find our E naught of the cell. Okay. Your cathode is still going to be your lead, and your anode is still going to be your aluminum. I don't think I wrote those down on my top page, but I can tell you that the cathode is minus 0.126, and your anode is minus 1.66. Right, so this is a case where if you had to look at your chart and say, which one am I going to make my anode, which one am I going to make my cathode? You want your more negative one to be the anode because that will outcompete the negative of the cathode. So it therefore makes your E naught of the cell positive at 1.53. Repeat my, yeah. So if you were saying aluminum and lead were used in an electrochemical cell, which one's the anode, which one's the cathode? You want your E naught of the cell to be positive. So if you're given lead and aluminum, you would have to look at your reduction potentials and say, okay, what's going to give me my greatest value for my E naught of the cell? Since both of these are negative, you want to pick your more negative reduction potential to be your anode, because that will then outcompete the negative from the cathode, creating an overall positive charge. Yes, and in this case, it's galvanic. And they told you that way. Yes. If you can make it positive, you want it to be positive. Yeah. Unless it tells you that it, right, is a cell that is supposed to be negative. But in this case, it's galvanic. It can be positive. Okay, so we found our E naught of the cell. That's not the hard part yet. The portion that becomes the challenge is we want the concentration of aluminum to change by 0.4 molar. So this looks at an ice table type of question. So if we write out an ice table, you're only worried about your ions. So you can just use your 3Pb3+, oh, sorry, 2+, and your 2 aluminum 3+. And we say that we're starting with concentrations of 1 molar for both of them. this is galvanic cell. We have a positive E naught or E naught of the cell, which means that we are going to be producing products. So we're saying that it's changing by 0.4, which means that we're producing 0.4 molar more of that aluminum. So our change here is going to be this 0.4, but only for the aluminum. We don't really know what it's changing for the E. And this we could write out if we're talking about x minus x plus x as +3 or +2x, because we have that coefficient of 2, right? Which just happens to be that 0.4. So we end up at 1.4. What would be your change for the lead in this case then? In terms of x, it would be -3x. Okay, and so our equilibrium is our question mark. We don't know what that is because we don't know what x is yet, right? We know that aluminum's changing by +2x, so we end up with 1.4. So we can say that 1.0 plus 2x is equal to 1.4. Right, 2x is equal to 0.4 is our change. So x is equal to 0.2. So what becomes our concentration for lead at equilibrium? 0.4, because we're saying 1 minus 3 times 0.2 is equal to 0.4. Yeah, you could just basically solve the aluminum first, use that x to find what your lead is changing by. Does that make sense how we use the ICE table to change it and solve for x? So it will end up equaling 0.4, because if we said, right, if we have 3 times 0.2, that's 0.6. So 1 minus 0.6 as our change would be 0.4. They're both 1, so it looks a little weird because it's the same. Okay, so now at equilibrium, we have 1.4 and 0.4. So now when we use our E cell or our Nernst equation, wow. We can now plug in everything that we know to find E naught, or to find E cell. So E cell is now the 1.53 that we just found. What's our N? Yep, N is 6. Our Q here we have to be mindful of because they both have coefficients. So our 1.4 is our aluminum. That's going to be on top. And that has an exponent of 2. And then we have 0.4 on the bottom, and that has an exponent of 3. And then you just solve this like you would any of the other 4 problems we just solved. So E cell would be 1.51. It's not too bad of a challenge problem. You just need to recognize what's that ICE table and change that you're working on. Huh? If it's on the practice exam, just make sure you recognize how to do it. But I wouldn't be too concerned with it. He's given you challenge questions before and said no challenge, so I feel like he would probably hold up to that as well. Yes. I don't think so. I think electrolytic cell is just a blanket term. Let me see what they call this one. I would check your notes for that. I don't remember off the top of my head. I think electrolytic cell might just be a blanket term, but I might be, it could be either, but check your notes before you take my word for it. I don't want to tell you the wrong thing. I know that there is a word for something that's negative, but I can't just remember what it is right now. Yeah. I don't do a lot with batteries. I do other cell stuff. Yeah. It was 1.51. Sorry. I got 1.515, so it rounded to 1.52. Okay, any questions? Alrighty, okay, I think that's it, and I will try to have some practice problems for you for your final as well. Okay, yes.
Questions. So here, when you have the two, why, like, what makes it?
So that's just like basic balancing equation stuff,
Okay.
right? We have 2 in our iron here, so you need to add 2 there. So that's where that comes from. Yep.
So then, here, to add the hydrogens, is it because you added 3 waters here, so you multiply
Yes.
this
Yep.
here. And then you add the electrons to the same side.
Yes.
So like here, you added the hydrogens to the product, so you added it to the reactant.
Yes.
I mean, to the same.
Yep, so in this case, we had to do that, but right in a couple, and like in this one down here,
Okay.
we have some charges on both sides. So you just want to make sure that you're adding your electrons to your more positive side of the reaction so that you can bring it down to the more negative side. Does that make sense? Right, you have something that's at 100 and you want to get it down to 0.
Okay.
So your more positive side is the one that's 100, so you need to add 100 electrons to get down to 0.
Okay. Okay. Yeah.
Yeah, does that make
okay,
sense? Or like,
yes.
again, right, or you can have something that's 0 and you have a negative 50. So you need to add negative 50 to the 0 side
So
to
that
bring it down to
okay.
negative 50.
And then here, I didn't finish the equation, but I was wanting to go back to yours, but the end part
Yes.
is still
Yep.
confusing.
Yep. So, very similar to like what we did up here, right? We said, yeah, up here. So, right, we said, okay, this has 6 positive charges. This has no positive charges.
Okay.
So let's bring it down, use this negative 6, right? We looked at everything on the reactant side, everything on the product side. Here, again, same thing. Everything on the reactant side, we say, okay, I have a -2 here. So it's an overall of -2 on the reactants.
Okay.
On this side, we had 2 +3s. So this thing has a +6, and I have -14 of these. This is -14. So overall, +6 minus 14 is -8. So we're comparing -2 to -8.
Okay.
And so since -2 was more positive than -8, we need to add some electrons to this side in order
So
to
it
bring
would
it
be
more negative.
6.
Yes.
Because it would be same.
Yes, yep.
Okay. And then this one, I didn't write, I think, the finished one, but how was it 1? There was only 1.
Yep, so in this case. In this case, this was question 9. So we were looking at like this guy here and then this guy here.
Okay.
So on the reactant side, we had 4 here, and on the product side, we had 3 here. So if we were to take these last 2 equations and add them together, it would be 4 and 3. So it's like saying you have 4x and 3x. So you would subtract 3x from this side to bring it to 1 on this side. So you're just doing 4 minus 3
Oh,
to
okay.
get to 1.
Okay.
Yeah.
Okay. And then for these, how do you know to like create that?
Yep.
Yeah.
So this one is like the half reactions. So if you broke
Okay.
this into the half reactions, if you said, okay, silver is what we did, what we did here, right? We said, okay, break this aluminum and lead into 2 reactions. We're saying, okay, a lead is going from silver, aluminum to aluminum 3+. So we need 3 electrons. We
Okay.
basically did that here without breaking them into the half reactions. We just
Okay.
said, okay, Ag is going to plus, but copper is 2+. So I know that this is going to be a 2-to-1 ratio, so I can just multiply this by 2 right away.
Okay, so but like, in order to like form it, like that
Oh,
AG
yep.
plus CU.
So we're looking at silver plus and silver here.
Mhm.
This is in your anode.
Okay,
So your anode has to be the oxidation reaction.
okay,
So we want to write this combination of stuff as oxidation reaction. So in order to make something oxidized, we have to give up electrons. So we have to go from the solid to the positive charge because we're giving up electrons in order to
Okay.
go from silver to silver
okay,
plus.
I got it.
Okay.
Okay, thank you so much.
Yeah.
Like,
Hey, so I didn't find any of yours in my stack. Was it just your exam 6?
Yeah.
Right? Okay, I looked through it right before I came. I will search through them
Unless I
again.
got it last time. Or did you get a new stack recently?
I should have gotten a new stack for exam 6, because that I got that before break. I don't think I saw you before break.
Okay.
Maybe I did.
Because I got a stack of
Yeah,
it,
I
I'm
know
just-
I
haven't
remember
looked.
giving you a stack. Check to see how many exams you have.
Okay,
It might be 5, it might be 6. I didn't
Okay.
see any of yours, so you might have them all together
okay,
already.
I'll email you if I can't.
Yeah,
find
if you
it.
can't, if you're missing one, just let me know and I'll find it. It's just,
Okay.
I might just missed it. There are a whole bunch of others, so
Yeah.
just let me know.
No worries, thank you.
And then Nora, I have her 2. I think you just need 2, right?
Yes,
Okay.
I should.
I think that was the only ones that your names that I
Yeah.
saw, so. I should get-
you.
Yep,
Do we get our exams?
when did you take it?
Or like just our exams in general?
Do you have extra time or do you just take it in class?
Or just take it in class?
You can- so
I'm
you
looking
can
to
always-
Review it.
You always can keep your review packet, or you
Okay.
can always keep your
Exam.
exam packet.
Just look at the answers.
So I would just look at the answer key, because I don't think I definitely don't, I just have your Scantron.
Okay.
If you need to see your Scantron for any reason, let me know and I can like show you that.
Yeah.
But you can just look at the answer keys at like the test and anything, you don't have your exam. Yeah, yep.
And for like my gradable class, I think I have like 2 B's and then like 4 A's.
Okay.
Without the one that's dropped.
Yep.
Would that like average out to like kind of an A?
Yeah, so I would say like it's a. You have A, and then B, so that's like 2/3 A, right? You have a 2/3 A, so you're like leaning towards the A, right? You're over the 50% mark for an A.
Okay.
So if you get another B or if you get an A, then like one of your B's will drop. You'll be on the good side of that. I think you're good. Yeah.
Okay, thank
Yep.
you.
Oh, okay. I have trouble with kind of using grade.
Yeah. Yeah, absolutely. Do you just want like, doesn't matter. Okay,
Okay.
yeah. Do you just want to know, I'll stop my Zoom.